The genesis of temperature measurement. For centuries, heat and cold were understood only as vague, relative physical sensations. This began to change in 1596 when Galileo Galilei invented the thermoscope. Galileo's device consisted of a glass bulb filled with air connected to a narrow tube immersed in water. As room temperature changed, the air inside expanded or contracted, pushing or pulling the liquid column. While revolutionary at demonstrating temperature shifts, the thermoscope lacked one critical element: a standardized numerical scale. By the early 1700s, scientists recognized that quantitative scientific progress required precise measurement scales. The first standardized scales emerged almost simultaneously from two independent researchers. Ole Rømer, 1701. The Danish astronomer constructed a scale based on two fixed reference points, the freezing point of saltwater brine, set to 0 degrees, and the boiling point of pure water, W, set to 60 degrees. On Rømer's scale, pure water froze at 7.5 degrees and human body temperature registered near 22.5 degrees. Sir Isaac Newton, extendeni, or one inquest working independently in England. Newton devised a scale using 0 degrees for freezing water and 12 degrees for human body temperature, dividing the difference into 12 equal units. In 1724, Dutch-Polish physicist Daniel Gabriel Fahrenheit refined Rømer's scale by replacing alcohol with mercury in his glass tubes. Fahrenheit multiplied Rømer's scale intervals to eliminate awkward fractions and stabilized his baseline using an equal mixture of ice, water, and ammonium chloride salt. His reliable mercury manufacturing process allowed the Fahrenheit scale to spread rapidly across Europe and America as the standard. Guillaume Amontons and infinite cold. While instrument makers focused on measuring everyday weather and body heat, French physicist Guillaume Amontons pursued a fundamental question: is there an ultimate lower limit to temperature? Between 1699 and 1702, Amontons designed an air pressure thermometer to study gas behavior. He discovered that as a gas cools down, it exerts less outward pressure on its surroundings. Amontons referred to this internal pressure as the springiness of gas. By analyzing the linear relationship between temperature drop and pressure loss, Amontons performed a theoretical extrapolation. He reasoned that if a gas were cooled continuously, it would eventually reach a point where it lost all elasticity and exerted zero pressure. Amontons called this theoretical lower bound, infinite cold. He became the pioneer of research into absolute zero, estimating that this absolute lower limit lay roughly a quarter of the way down from the boiling point of water toward total absence of pressure. Gas expansion laws and theoretical extrapolations. A century after Amontons, experimental chemistry advanced significantly. Scientists could isolate pure elemental gases rather than relying on ambient air. In 1787, French scientist Jacques Charles filled 5 identical balloons with equal volumes of different gases, including oxygen, nitrogen, and hydrogen. Upon raising the temperature of all 5 balloons from 0 degrees Celsius to 80 degrees Celsius, Charles observed that every balloon expanded by the exact same proportional volume. In 1802, chemist Joseph Louis Gay-Lussac published these findings, officially formalizing them as Charles' law. Gay-Lussac expanded the experiments across wider temperature ranges and determined a crucial ratio. For every change of 1 degree Celsius above or below 0 degrees Celsius, the volume of a gas expands or contracts by approximately 1 out of 273 till 1/273rd of its original volume at 0 degrees Celsius. By extrapolating this linear rate downward, Gay-Lussac calculated that if a gas dropped 273 degrees below freezing, its volume would mathematically contract to 0. He published an initial calculation of absolute zero at approximately -266.66 degrees Celsius. However, Gay-Lussac explicitly highlighted a fundamental flaw in using gas expansion to define absolute zero. Real gases do not remain gaseous indefinitely. As temperatures drop toward extreme lows, every gas transitions into a liquid or solid phase. Once a phase change occurs, gas expansion laws no longer apply, rendering gas volume extrapolation an incomplete model for absolute physical cold. William Thomson and the absolute thermodynamic scale. Overcoming the phase change barrier required an absolute scale derived from energy thermodynamics rather than material expansion. This breakthrough was achieved by British theoretical physicist William Thomson, later known as Lord Kelvin. Thomson was an extraordinary academic prodigy. After graduating from Cambridge University at age 21, he moved to Paris to gain experimental experience under French physicist Henri-Victor Regnault. In 1846, at just 22 years old, Thomson was appointed chair of natural philosophy at the University of Glasgow. Thomson was deeply interested in unifying all matter, forces, and energy under universal laws, influenced by James Prescott Joule's discoveries. Regarding the mechanical equivalence of heat, Thomson focused his attention on absolute cold in 1848. He published a landmark paper titled On an Absolute Thermometric Scale, founded on Carnot's theory of the motive power of heat. Thomson proposed bypassing specific material properties such as mercury expansion or air volume, and instead setting a temperature scale based entirely on the thermodynamic engine cycle developed by Sadi Carnot. The 1848 model. Thomson established that the ratio of mechanical work to heat output in a Carnot engine depends strictly on temperature. On this scale, equal units of temperature represented equal amounts of mechanical work performed by a unit of heat descending between two thermal bodies. The 1854 revision, when experimental steam data from his former mentor Henri-Victor Regnault revealed small discrepancies with Thomson's initial 1848 mathematical equations, or MESTEL, Thomson refined his approach. In an 1854 paper, he redefined the scale using the mechanical equivalent of thermal energy, divided by Carnot's function, by fixing the distance between the freezing point and boiling point of water at exactly 100 units, an absolute Celsius scale. Thomson derived the precise physical point where heat energy reaches absolute zero, minus 273 degrees Celsius, and modern precision defines this at minus 273.15 degrees Celsius or 0 Kelvin. The legacy of Lord Kelvin. William Thomson's thermodynamic absolute scale provided physics with a universal measurement system independent of substance behavior. In 1892, in recognition of his monumental contributions to thermodynamics, including his co-discovery of the Joule-Thomson effect, Thomson was raised to the British peerage. He took the title Baron Kelvin of Largs, named after the River Kelvin that ran past his university laboratory in Glasgow, Scotland. Today, the Kelvin scale remains the baseline standard across physical sciences, defining the absolute energy states of the cosmos from deep space to subatomic quantum physics.